This lesson is for day 2 of section 5.3. We are going to be solving applications of what we were working with yesterday. So everything here is going to be a quadratic related to a real-world problem. Number 1 is a pretty standard question that we're going to ask you. This question says that a ball is thrown into the air with an initial velocity of 15 feet per second. The ball was 5 feet off the ground when it was released, and this equation models the height of that ball at any time. How long does it take for the ball to hit the ground? So this tennis ball is going to basically take a parabolic curve. It's going to rise and come back down to the ground. So this is where the height is 0. And when it was released, this distance here is 5 feet because he throws the ball 5 feet off the ground. Now we're trying to figure out the overall time it takes for this ball to take this path. So basically, when we look at this function here, we want to plug in h is 0. When h is 0, that's when the ball hits the ground. So this is really the key thing for this question, is to realize that the height is 0. Alright, so we set up our equation. Negative 16t squared plus 15t plus 5 equal to 0. And now I'm just solving a normal quadratic. When I look at this, I don't see that it's factorable. So I'm going to use the quadratic formula. Okay, so here I have the quadratic formula shown, and you guys will be doing this with and without a calculator. Today I'm going to show you how to put it into your calculator, but for most of your questions, especially in your homework, do not use a calculator, but occasionally on a test or a quiz we might allow you to use a calculator for some of the more difficult computations. Alright, so when you plug this in, you can do this all at once, but let's think about first just doing the discriminant. So I'm going to do 15 squared minus 4 times a. Make sure you put parentheses around everything and the correct, a minus sign here but a negative sign here. You should get a positive because this should have real world solutions, because it does take a certain amount of time for that ball to hit the ground. So we get positive 545. Now, I want to talk about this before you continue to solve this. If you have solutions, negative 15 plus root 545 divided by negative 32, and another solution of negative 15 minus the square root of 545 divided by negative 32, this one will actually give you a negative solution overall, because you have a negative number plus a larger, the square root of 545 is larger than negative 15, divided by negative 32. So overall you'll have a positive number divided by, positive divided by a negative, which means overall you'll have a negative here. So we actually only want to use this because this is not a real world solution for this problem. So a lot of times you are going to throw out in an application problem one of the solutions because it doesn't make sense in the original problem. This should have a positive amount of time because time can never be negative. So that's why we're going to use this one here. And so we have negative 15 minus the square root of 545, and then we're going to divide that by negative 32. And we get positive 1.1982 seconds. So I'm going to write out at least to 4 decimal places here. So I have time is equal to 1.198. I think if we rounded it was 83, and that was seconds. Okay, so that's how long it takes for the ball to hit that ground. In number 2, an open top box is made by cutting 3-inch squares from each corner of a square piece of cardboard and then folding up the flaps. The volume of the box is given, and it's 1,083 cubic inches, and we're supposed to find the dimensions of the original piece of cardboard. So we want to know what the original dimensions were of the square piece of cardboard, so the number should obviously be the same. Alright, now when you look at this question, you're going to have to draw a picture to help you visualize. So we start with a square piece of cardboard. So let's say each side here is x units long, and then we're going to cut away a little square piece from each corner, so we create little flaps so that we can basically fold this box along these lines here, fold it up to create a cardboard box. Okay, so each of these is 3 units long. So in other words, this new dimension of this side here would be x minus 6, okay, because we take away this 3 and this 3 on both sides. It's going to be the same here. This will be x minus 6, and this portion here will also be x minus 6. Alright, now I'm just showing you that so that you can kind of help visualize what it would look like. Essentially, you're going to create a box that looks like this by folding up those sides. This height would be 3, going all the way around. All of those pieces here would be 3. And the dimensions of the base here would be x minus 6, so this side length here. And this would also, going across here, would be x minus 6 as well. Now you know that the volume of a box is simply length times width times height. That's something that you've known for a long time. And we're just going to use now this drawing and replace the length, the width, and the height here, and we are going to get a function. Now, the length and the width of the box is both x minus 6 and x minus 6, and our height is just 3. So we're using these dimensions, length, width, and height here. And we also know that the volume in this first sentence here, the volume is 1083 cubic inches. So I'm going to set that equal to 1083. Now some of you guys are going to want to solve this quadratic here, you're going to want to distribute all of these terms here and FOIL that, but you actually don't need to. Let me rewrite that a little bit cleaner here. I'm going to put the 3 on the outside and write that as 3 times x minus 6 squared. So now this is an easier question because we don't need the quadratic formula, we don't need to factor this, we can simply use the square root method. So I'm going to divide by 3 first, okay, to get 361 is equal to x minus 6 squared. There we go. And now I'm going to take the square root of both sides. When I take the square root of both sides, remember you're going to have positive or negative root 361 equals x minus 6. Now the square root of 361, that's actually a perfect square. So this is positive or negative 19 equals x minus 6. I'm going to move that 6 over to the other side so that I have x equals 6 plus or minus 19. Obviously, I would get 2 different solutions here. One is 25 and one is negative 13. Because it's a square box and because it's a distance, the length, we can't have a negative, so we're going to use x equal to 25. So the original piece of cardboard was 25 by 25 inches long. So the cardboard box was 25 inches by 25 inches. So those are the dimensions of your box. So when it asks for dimensions, it means this. Okay? Problem 3 is a question that you also want to use a diagram for. It says the homeowner wants to install a deck around her swimming pool. The swimming pool is a rectangle and measures 25 feet by 32 feet. The deck is to have the same width all the way around the pool. What should the width of the deck be if she has 310 square feet of decking material? So I'm going to draw the pool first. This pool here is going to be 25 by 32 feet. Doesn't really matter what I label 25 and 32. Alright, now she's going to create a deck all the way around this pool, and the distance, the width of this deck, is the exact same. So basically the distance from the edge of the pool to the deck, let's label that x. It'll be the same all the way around the entire pool. So let's talk about what the area of this deck would be, because that's what we're told we have a limitation on. She only has 310 square feet of the actual decking. So I want to find the area of the deck. Okay, once I find the area of the deck, how to express that, I can set it equal to 310 square feet. So the area of the deck is going to be found by taking the area of this entire deck length and width, and then subtracting out the area of your pool. That will leave you with everything. I'm going to color it in red, but that would leave you with all of this decking, what I just colored in red, by taking the area of the entire rectangle and basically subtracting out this pool area. Okay, so let's express that. Alright, so the length of this pool, the deck, we already know the length of the pool, but the length of the deck, we're adding an x here and an x here to an existing 25. So that means that this deck length would be 25 plus 2x. Okay, and our width, same thing, is going to be 32 plus 2x, because we're adding a unit of x and x on each end in the original length of that pool, or width of the pool. So now that area of your deck is going to be found by multiplying your length times your width. So 25 plus 2x multiplied by 32 plus 2x. That would be the entire area of the entire big rectangle. And now we're going to subtract away the area of your pool. So the pool area will be subtracted away, and that's going to be 25 times 32. So this is the area of the overall deck. Alright, so now what I'm going to do is work on actually foiling this out, because I do have this whole part that I need to subtract away. So I'm going to find out what this is going to equal. And when I FOIL this out, and you can check this yourself, I get 4x squared plus 114x, and then another term that's going to be 32 times 25. Okay. Remember, we're also subtracting away 25 times 32, so I'm just going to cancel these out, and it leaves me with just 4x squared plus 114x. So that's the area of your deck. Now, she is told that, or we are told that she only has 310 square feet of decking, right? So our area has to actually equal 310 square feet. So I'm going to plug in 310 here, and now I have this equation to solve. Okay, this is a quadratic now, and I have three terms, so I can't use the square root method. This is also not factorable, so I'm going to be left with the quadratic formula. I can make this a little bit easier on myself though by factoring out a 2 here, because each one of these terms is has a common factor of 2. So if I do factor that out, that has no effect on the overall solution. So even if you didn't factor this out, you would still get the same exact solutions by using this quadratic or this quadratic. Okay. Alright, so I set up the quadratic formula already, and I'm going to put that in my calculator. And I'd like you guys to do the same just to make sure you can do this correctly in your calculator. The discriminant here is what I like to calculate first. Okay, and after I stick all this in my calculator, I end up with x equaling negative 57 plus or minus 67. So this discriminant, after I take the square root, is just a positive 67, and then divided by 4. So I'm going to look at these solutions, and I'm going to throw out the one that's negative. This, of course, gives me an overall negative answer, negative solution, and I can't have a negative width for my deck, so I'm going to throw that one out. So I want to know what negative 57 plus, or what negative 57 plus 67 divided by 4 is. And that gives me 10 divided by 4, which is 2.5. Okay, so in this case, she needs 2.5 feet, the width of their deck. So width of deck is 2.5 feet all around. Okay, to keep within the constraint of having a total area of 310 square feet of decking. Okay, last up we have problem 4 here, and again I'm going to draw a diagram to represent this. So a farmer wants to build a rectangular fence near a river, and he has 120 feet of fencing. We want to know what the largest dimensions of, what the dimensions for the largest region that could be enclosed if one side of this rectangle is not fenced, because you're going to be using the river. So in other words, we have this river here. Okay, and he is going to enclose using a rectangle a certain region, and one of the sides is not going to be used because he doesn't need fencing here along the river. So let's label, if we know that he has 120 feet of fencing, let's let x be one side. That means that the other side has to be x, and then left over, because we only have 120 feet total, that width here is going to be 120 feet minus the 2x. So this represents the leftover fencing if we let each of these sides be x. Okay. Alright, so let's look at the area of this shape. So if we want to find the area inside here, we have to multiply the length times the width. So that's pretty easy to do. So the area here is going to be x times 120 minus 2x. So I end up with a quadratic, negative 2x squared plus 120x. So I just switched around the order basically after I distributed, and I'm left with this parabola. Now this is a parabola that would open downward, like so. Okay, we want to figure out, this parabola represents the area, right? Well, if you think about this graphically, the area, the maximum area, the largest region, is going to be found right here, okay, at the vertex. The maximum of this parabola would give you the very largest region that can be enclosed using 120 feet of fencing. So that's what we're going to do. We're going to try to find the maximum. Now, eventually, we're going to give you an algebraic way to calculate this, but for right now, we're just going to ask you to use your calculator. So you can plug this into your calculator and search for the maximum of this parabola. Okay, so go ahead and plug that into your calculator, like I did here. And when you go to graph this, I already adjusted my window, but when you graph this, you're going to get a parabola here, and you're going to find this vertex. So we're going to hit second calc, and then scroll down to maximum. And it will ask you for a left bound, right bound. Remember, you're just going to the left of that vertex, hitting enter, and then going to the right of the vertex and hitting enter. And when it asks you to guess, just hit enter one more time, and we get a maximum of 30, 1800. So let's talk about what that means, that vertex. So we get a vertex here of 30, 1800. All right, now this is your x input, and this output here is the area. Remember, we let area equal essentially the y. And this is what that y represents here. So we have area. And so basically we know that the max area is 1800 when we use an x value of 30. Okay, so if the width is 30 feet, that makes the length, if I plug in 30 into here, I get 120 minus 60. So I get 60 for the length. So if the width is 30 feet and the length is 60 feet, the farmer gets a max area of 1800 feet. Square feet, I should say. Okay? Okay, so that is the end of the lesson. This is just an application of using our idea of maximums or minimums as well. So be prepared to answer any type of these for application problems. Nice job. I'll see you in class tomorrow.